We're going to continue to look at relationships between variables that aren't linear. Specifically, we're going to focus on exponential models. And exponential models are models that are in the form of y equals a times b to the x. Notice the variable here, x, is in the exponent. Common examples that you might be familiar with for exponential models are exponential growth with compound interest and exponential decay with radioactive decay. We can take this exponential model and we can make it be transformed into a linear model if we take the log or natural log of both sides. And then if I apply properties of logarithms, I can change this product to a sum of two logs, and then I can use the power property to pull the exponent out in front. So ln of a, natural log of a here would be our y-intercept, and natural log of b would be our slope. Let's take a look at some examples. This is on your handout of notes. We can see that fees at the University of Arizona have been growing, I would say, exponentially. It started off at $89 and now in 2011 it's $913. And what that indicates to me is that they're charging for a lot of extras, like maybe now there's an internet use fee, an athletics facility use fee, all sorts of fees. And so this is probably exponential growth, but let's use our calculator first of all to look at a scatter plot. In list 1 I've entered the years, and in list 2 the fee. I already have my scatter plot turned on with list 1 and list 2. Let's just do zoom stat. And clearly this is not a linear relationship. We can see it definitely curves and started off somewhat slowly, but now it's growing a lot more quickly. So I think an exponential model might be a good relationship here. Let's actually take the natural log of the fees list, so the natural log of the y's. I'm going to come over here to list 3, and I'm going to define list 3 as the natural log of list 2. And if you think about it, the opposite of exponential is logarithmic. So if you think about it, what we're doing here should make sense too. To transform this, if I take the log, it's going to straighten it out. So let's take a look at a scatter plot now of the year along with the natural log of the fees. Zoom stat again. That looks a little bit better. Still not perfect, but definitely more linear than what we had before. Let's calculate the least squares regression line and look at a residual plot for this. So to do a least squares regression line, I'd go to Stat, Calc, Linear Regression. I'm going to use list 1 and list 3 now. And I'll come down here to Calculate. And let me write down that equation. The equation would be natural log of fees hat equals 0.332 times year. And remember, our year is actually the number 4, 5, 6, 7, 8, 9, 10, or 11, corresponding to the first number of the year in our list. And then our slope is about, or excuse me, our y-intercept's about 3. So let's actually do a scatter plot of the residuals and see what that would be like. I'm going to hit second stat plot and change this to be a plot of the residuals. And remember, every time you do a linear regression, a new list of residuals is actually calculated and stored in the list called resid. Now I'm going to do a zoom stat, and there seems to be random scatter here. Okay. So this linear model might be appropriate. Let's try a different model. Let's try a power model. To do this, we need to actually take the log of both the x's and the y's. So in list 4, I'm going to list the natural log of the year. And let's take a look at a scatter plot for that. I'll come back here to my original scatter plot, and I'm going to have as my x's now be list 4 because that's where I have the natural log of the year, and my y's is list 3. That's the natural log of the fees. Let's do zoom stat. I don't know, that seems somewhat curved, maybe not quite as good as what we had before. So let's actually run a linear regression on this and see what we get for our equation and for our residual plot. So stat, calc, linear regression. Now my x's are list 4 and my y's are list 3. I'll come down to calculate. Okay, so there we'd have as our equation natural log of fees hat equals 2.26 times the natural log of year plus 1.054. So let's take a look at a residual plot before we decide whether we think an exponential model or a power model might be better. I'm going to make a note here about the correlation coefficient. The correlation coefficient is 0.956. I didn't notice what it was before for the other model that we looked at. Hopefully you noticed that. I might go back there and take a look at that in a minute. But let's do our scatter plot of our residual. So second stat plot. And I'm going to change this list to be residuals. And zoom option 9. Once again, there appears to be, well, I don't know, this might have somewhat of a pattern to it. We're high and then we're down here below and then up. Right? So which model do you think might be better? I'm going to go back in a second here. I'm going to pause this. I'm going to go back and calculate the first model again just so I can get that correlation coefficient. So I went back and did that first model again, plotting year on the x-axis and natural log of fees on the y-axis. And here the correlation coefficient is 0.981, which is a bit higher. So I'm thinking actually that this particular model, our first model that we looked at, the one from B, would be a little bit better. If I wanted to actually see if there was a statistically significant relationship, linear relationship, once I've linearized my data, I could do a hypothesis test on the slope of each of those if I wanted to. So using the model that we just chose, which is the first model, which is the one right now that I have on my calculator, would you predict, your prediction be too high, too low, or just about right for the 2012-2013 school year? Let me go back here and actually have my calculator store the equation in Y1. I didn't do that before. Let's do that so we can use the equation here to actually figure out whether it's going to be higher or lower. I have a feeling it's going to predict too high because exponential models tend to, like all of a sudden once you get them going, shoot off wildly. So I have a feeling it's going to be too high for the 2012-2013 school year. Let's take a look at what it might be for the 2012-2013 school year. I'm going to go to second table, and actually here's what I'll do. I stored the equation in Y1. Let's do vars, y vars, and I want to evaluate this for the 2012-2013 school year, so I'm going to do 2012. Okay, now remember we had our model linearized, so I actually have to transform this a little bit. This is what we get when we do 0.332 times 12 plus 3, and that's actually equal to the natural log of fees. So I actually need to do e to this power to get the fee. Okay, maybe that'd be just about right. I thought it might be on the high side, but I'm guessing it'll probably be off, if we were to go 25 years into the future. Let's just do that for a second. I'm kind of curious what would happen if we were to try to extrapolate far away from the model. Extrapolating for 12 is just the next year, so that's not too far off. But let's see what happens if we do this for year 25, 2025. What would the fee be at this school? And remember, we have to use base e to this power, which actually is already a huge number with our scientific notation. Yeah, it's so big that it overflowed the calculator, so that's not so good. So this exponential model clearly is not something we want to use to extrapolate far away from our initial values, but using it for the year 2012 seems like it might be reasonable. All right, let's take a look at another example. So let's go back to our notes here. I actually went through all of these questions. Let's take a look at this one. So a student opens up a bag of M&Ms and they dump them out, and they ate all the ones with the M on top. So when you dump them out, some will have the M right side up, some will have the M right side down. So he ate all the ones with the M right side up, puts the remaining 30 back in the bag, and repeats the process over and over again, eating the ones with the M's right side up until they're all gone. This table shows his course, so in the number of M&Ms remaining. So after he was done with the first process, he had 13 M&Ms remaining, and after he did this a second time, 13 M&Ms remaining, and so on. So take a moment and enter the course number in list 1 on your calculator and the number of M&Ms remaining in list 2. Okay, so I've entered the data in my calculator. You can see that. Hopefully you've done that too. And let's take a look at a scatter plot of the data and see if we can figure out what's going on, if it's a linear relationship, exponential, power model. So we'll go down here. X list will be list 1. That's our course number. And Y list will be list 2. That's the number of M&Ms that are left there. So zoom. Oh, let's clear what's in Y1 here. Zoom 9, zoom stat. Okay, this clearly is not linear. As a matter of fact, it looks like it's exponential decay because it looks like it's asymptotic, although technically not quite asymptotic because we do get to 0, but obviously we can't go lower than 0. Although maybe this person could take forever to actually get that last M&M eaten because maybe it doesn't want to show an M right side up. But I would say maybe an exponential model for this. So with an exponential model, we're going to take a natural log of the Y values. So I'm going to go to list 3 and say, let's take the natural log of list 2. Domain. Why do we have a domain error? Well, if you actually read the directions, notice here, we actually need to remove the last point because the natural log of 0 is undefined. So let's try that. So I actually need to go and delete that value in list 2 first. And I'll go over here and delete this value as well. Now let's actually go to the very top again for list 3 and call list 3 the natural log of list 2. And you could use log base 10 if you wanted as well. Oops, list 2. Let's take a look at a scatter plot of the transform data. That looks much more linear than what we had before, and actually that is what we have right here as well. So now it's much more linear than what we had before with the transform data. All right, let's continue on looking at the notes. Here's the Minitab output from a linear regression that was done on the data, and notice our R-squared value is pretty high when we transform the data and we have natural log of remaining. So let's write our equation here. Our equation would be natural log of remaining, and I'm just going to use REM for remaining, and that's hat equals, we'd have our slope, which is, or our y-intercept, which is 4.0593, plus our slope, which is actually a negative, I should have put minus there, negative 0.68073 times the course number. So times the course number. So that's our regression equation for this from the information that's given on the computer printout, with the constant being the y-intercept and this other number being the So now we're ready to use our model that we had back here to make a prediction. We want to predict the original number of M&Ms in the bag, and that would occur when our course number would be 0. So negative 0.68 times 0 is obviously 0. So then I'm just going to have natural log of the remaining, which actually in this case our remaining is what we started with, equals 4.0573. And then to transform this and change this from logarithmic notation to exponential notation, I'm going to rewrite this as e, oh, don't want to forget my hat here, e to the 4.0573, and do that calculation on my calculator. And when I do that calculation on my calculator, I get that initially there was 57.93. Now if we assume that M&Ms are equally likely to land with the M side up or M side down, an exponential model makes sense because we should have half of them disappearing each time. So if we take a look at, if we go back to our original list here, we can see that we had 30, and if we're going down by about half each time, initially there would have been about 60. So this model is not too far off here with about 58 M&Ms. So now let's calculate a confidence interval for the slope of our transformed data. Our slope for the transformed data was 0.68073. And then we're going to need to use a t star value. Our t star value, now be careful here, I just realized we actually now have only 6 data points, so we're going to use a t star value with 4 degrees of freedom because we got rid of that last data point since we couldn't take the natural log of 0. So our degrees of freedom is actually 4. So I'm going to pause this for a second to look up my t star value. So my t star value was 2.776. That's based on 4 degrees of freedom and a 95% confidence level, 2.776. And then I'm going to multiply that by the standard error of the slope, which if we go back here, we can see that the standard error of the slope is this value right here, 0.04755. So we've got our point estimate plus or minus our margin of error, and I'm going to pause it here so I can do the calculation. So I've calculated my confidence interval by adding and subtracting the margin of error, and so I can say I'm 95% confident that the slope of the regression line relating course number to natural log of the number of M&Ms remaining is between 0.5487 and 0.8127. And so remember, this is an exponential model. And remember, exponential models are y equals a times b to the x. And really here, if this was exponential decay and we were having half M&Ms each time, we'd expect this value to contain the number 1/2 in it, and it doesn't. So what does that mean about our confidence? Or not so much our confidence, but what does that mean about the M&Ms themselves? Would they be good for using as a 50% chance? In other words, would they be as good as, let's say, randomly choosing between even and odd numbers in a list of random numbers? Will we expect to get half M's up on average? And it looks like actually we end up with a little bit more than half M's up, or actually M's, I should say M's down, because we're talking about the ones that remain. But it's not half each time. If it was half each time that are being eaten, we'd expect to see 1/2 in this confidence interval. If you have any questions, please make sure to email them to me, write them down, bring them to class on Monday.